Hello, my name is Juliano. I'm an embedded software engineer at Sensata Technologies, and today I'd like to talk to you about virtualization for embedded systems, and more specifically how it's become more common in the embedded world. So for today's agenda, I'd like to touch bases on what is a container, issues with containers using namespaces, specific issues related to embedded systems, solution that we have for embedded system, and the benefit of those solutions. And at the end, I would like to give a quick demo of a virtualized system running on a Raspberry Pi. So to start with, we need to understand what containers are. Containers are a solution to a problem of deploying software in different computing systems or different computing environments. This is accomplished by creating a package which bundles the application binaries, libraries necessary, all dependencies, configuration files, and so on. And the type of container that I'm talking about is the one that basically create kernel namespaces, which are used to provide isolated workspaces. So every set of container is a set of namespaces. So every container then that you creates an isolated workspace that has a limited access to just its own namespace. That means then that the kernel then is shared among those different namespaces. And actually that's where the problem comes. So creating containers based on namespaces poses a problem. It means that the kernel is shared among all those containers, and to access the kernel then there's a syscall API that is very big and very difficult to secure. It makes it easy for applications running on containers to make use of the access to the kernel, to exploit it and run malicious software and take control of the rest of the system. This is a well-known problem actually, and a lot of guidelines to prevent this problem are already in place. Hardware virtualization is the one always recommended, and in fact very often we will find hardware virtualization coupled with containers. In the embedded world, we have even more specific problems when using namespaces as containers. One of them is mixed criticality. Very often in embedded systems, we have mixed criticalities, or different applications that have special needs and different criticalities on its own. So for example, the infotainment system on your car may be running in a different criticality than some other system that is able to connect to the COM bus. And you don't want the infotainment system crashing and taking it together another system that connects to the COM bus, because those COM bus systems are essentially connected to a lot of other important and critical system of the vehicle. Or even worse, something that has actually happened before, when hackers enter through the infotainment system of a car, and through that they were able to connect to a different firmware that had access to more critical lines in the car, and were able to then mess with the rear view camera of a car while a driver was backing up. That caused a crash, of course. There are other examples that don't involve infotainment systems. If we go to drones, for instance, we can have a drone that typically will stream video through a mobile device, but also you have a navigation system there. And we don't want the streaming of a video crashing and taking it together the navigation system, because of course, if the video is not working, we still want the drone to land safely. And another issue is the resource utilization protection problem. Because all containers are accessing directly the kernel, it's very hard to prevent different containers to overuse the CPU or memory, making it very easy for malicious software running on specific containers to access the kernel and just use all the CPU, all the memory, and crash the whole system. We also have the problem of real-time support that is not supported when using containers. Because, again, we are using the same kernel space, we are only able to then use a real-time operating system if that kernel supports that. But the reality is that sometimes we do want a real-time operating system for some applications, but sometimes we don't need that. And let alone use an RTOS, that is really difficult when using namespaces. So the solution for the embedded systems, much like other systems, is to use virtualization. This is called hardware virtualization type 1 or bare metal virtualization. It basically is an abstraction software that sits on top of microprocessors or the SoC and abstracts the hardware and software, making it possible for us to run different OSs and completely separate the resources they are capable of accessing. This really restricts the access to resource of each individual VM or virtual machines, and that brings a lot of features that we are going to look at now. And so by using the hypervisor, and that's what's called a layer of software that we put on top of the microprocessor, we'll have isolation and security. This means that now it's much more difficult to gain access of another container that is located in a different VM. If we have our infotainment system running on a VM that gets hacked, it will be very difficult for a hacker to go from there to accessing another firmware running in a different VM. We can now support mixed criticality. Now we can have different scheduling running in different VMs. We can have a Linux kernel running in one VM and even an RTOS running in another VM with completely different criticalities. We can now deploy separately all the units. We can deploy those VMs independently of each other and no longer need to worry about how they interact with each other. We have more resilience now. So if one VM crashes, the other one will still remain there working perfectly. We can vary our boot times. Now, because we are in different VMs, one VM can boot faster than the other according to their criticality. We can also virtualize coprocessors, not only the microprocessor, but let's say we have GPUs connected to your hardware. We can also virtualize that. And so now I'd like to show you a hypervisor running on a Raspberry Pi. This video was recorded yesterday and I will talk you through it. So basically what I have here is a Raspberry Pi connected to the UART interface. And the reason why I have that is because I want to show the boot up process. And more specifically, I want to show that we are not booting up a typical Linux system, but rather we are booting up a hypervisor. So I will go up there and I will show you at the start of the boot up that we are actually booting up something called Minus, and that's a hypervisor project, open source. And straight after that, I'll show you also there that we are then creating a VM, and that VM then contains the Raspberry. The reason why I'm using Linux is just for the purpose of this demonstration, but I could be using an RTOS or anything else. But really, this just makes it easy for us to run the first VM as a Linux-based VM, and from there we can generate other VMs, and that's what I'm going to do. So I'm going to check now here the IP address of that Raspberry Pi and start accessing it in 3 different windows. The reason why I'm doing that is because I want to have one window to create the VMs, and the other 2 windows I will use to log into them. So there I logged into the first Raspberry Pi section, and then we're going there to the 3rd SSH section to the Raspberry Pi. And once I finish that, then we're going to use a helper script that comes with the Minus project to create those 2 VMs. So there you go. This is the help script that I'm going to run. I'm going to, for the purpose of this demonstration, start with a 32-bit image, and then later a 64-bit image. And then when we log into those machines, we'll be able to see that they're actually executing different images. And so the way we're going to log into it is because Minus routes the output of the console to /dev/pts/one number there, and this is and we start with 3. So we log there, and we can see that the version of the distribution that we are using there is 32-bit, and now we're going to create a second VM, and that VM now is going to be a 64-bit, and so now we can log into that, and we should see that the version now is different than the other VM. So we have then 2 VMs running. One VM is a 64-bit and the other a 32-bit. So now I'm going to do something very interesting. It's something that we talked before here, which is the fact that overloading one VM will not affect the other one. So basically I'm creating 4 loops there that will overload the CPU. Hopefully will be above 80% of CPU usage, and we will then compare the usage of the CPU on the 64-bit machine to the 32-bit machine, and as we can see there, we are going to go over 80%. And now we can check the other VM, and we'll see that nothing has changed there, so the CPU usage is pretty much the same. So there you have it. It's a very brief demo and explaining the usage of virtual machines in embedded systems and how that can help us protect our different environments there. Well, thank you so much for your time.
Fantastic. Now we have a number of sponsored promos that we would like to share with you. They are from Rapid7, Signified, Flexera, Allstate, Instill, and last but not least, Sensata.